Yo, what's up, everybody? Welcome to my YouTube channel, or welcome back if you're already a subscriber. But today, what I'm gonna be teaching you guys about is how to make your own programming language and compiler in C#. And just to show you my programming language, I was able to I'm not finished with it yet, but all of it is written in my own programming language. That's just the string class, and then that's a script. And that just prints out a message box. But for this tutorial, all you need is your C# compile or your C# IDE, such as Visual Studio, or I'm using Sharp Develop. And the other thing you'll need is this program called OllyDbg. You could just Google it; it'll certainly come up. First thing, OllyDbg, OLLYDBG. I'm not gonna put it in the description, but then you could just click on download and then download it right here. And it's 1 megabyte. It's very, very compact, and it's just this. And then another thing that I would recommend is, this is just a recommendation because when you're making your programming language, this kind of knowledge, it's not just this, but what I would recommend is having some knowledge in assembly. Now, it's not only about knowing assembly, but when you learn assembly, you kind of learn things such as, like, you kind of figure out, like, why, for example, integers in C#, you figure out, like, why they're 4 bytes, why it's important, and whatnot, and, like, that kind of information is important. And if you do want to learn assembly, I was able to learn it in, like, 2 or 3, not learn it completely, not nowhere near, but I was able to get a very good understanding by watching this. If I could find the tutorial right here, it is on this YouTube channel. And yeah, here's the tutorial. It's a very good tutorial. You could just search up flat assembler on YouTube and it'll come up. And it's introduction to 32-bit assembly part 1, moving numbers around. But anyway, I have one more thing to say before we start, and that's that this is a tutorial, or this series is going to be a pretty advanced one. I will be putting in most effort, to be honest, but there are a lot of things, and especially in this first video, a lot of things can be really, like, overwhelming and difficult. But I believe after this video, after we get this first thing out the way, it'll be smooth sailing from there. But the first thing we're going to be doing is learning about the portable executable, and I'll get more into that as soon as we create our application. So it's going to be a console application, and you could just call it whatever the name of your programming language is. That's what I suggest you name your application. I'm just going to call mine programming language because I'm just making a tutorial. I already got my own. Mine's called Arrow. And I will be updating this on GitHub. I'm not sure if I'm going to have the link immediately, but I do have it open on GitHub. This tutorial. And right now I'm just saying the class how I like my classes. But anyway, to start off, the first thing we're going to be doing is, say you have an executable file. This is just some random executable file, and it runs, and then it closes immediately, and my computer breaks. Like, not really, but as you can see, it runs. Doesn't matter what executable file, any executable file on Windows. If you open it in text, and by the way, I also recommend you do have a good text editor for this. You don't need it because I'll be showing it all myself, but if you do want to check things out yourself, then I recommend Editor. But anyway, as you can see, when you open it, there's a lot of bytes. And the first 512 bytes of a file, and the number's 512 because every single section in a executable file is 512 bytes. So the first 512 bytes, which is this much, is something called the portable executable header. And to break it down, the portable executable just means it's a executable file for Windows that runs like that. And header, what a header is, it's not just for portable executables. There are very many file types that have headers, and all it is it's some data at the start of the file that tells you what to do with the file. When I was making my own file type in an earlier series, the operating system series, I made a header, and my header was only 1 byte, which would be this much. Because it wasn't that, it was just a font. Well, for the portable executable, it also needs things like backwards compatibility with like really old versions of Windows. So it ends up being 512 bytes. It's a lot of information on there. Some of it not that important, but nonetheless, we're gonna have to write all of it. And yeah, so to start off with, we're gonna make an enum in our thing. So add a new class to your project. Call it portable, or like we'll call it PE header. And it's not actually gonna be a class though, because it's gonna be a struct. So just change that to struct, and then I'm just gonna set this up. And the first thing we're gonna do is import system .runtime.interop services. And what that's gonna let us do is it's gonna give us access to an attribute called struct layout. And we set to layout kind .sequential. And what this is going to do is, as you can see, in this header, as I said, there's 512 bytes. And the way it works is that for every few of these bytes, there are variables. So like these 2 bytes are 1 variable. These 4 bytes could be 1 variable, and so on and so forth. What we need to do is make sure that these variables are in order, so when they print them out in memory, it's going to be in this order. So we got to make sure it's in order by making it layout kind.sequential. And yeah, and one thing before I do start this struct, this struct is going to have a lot of variables in it, which technically you're not supposed to do. It breaks one of the rules of structs. There are like 3 or 4 rules. But the thing is, there are some things like the rectangle struct in system.drawing that was made by Microsoft. It breaks all of the rules. So I don't really see that much of that important to actually follow the rules, because if Microsoft's breaking them, it kind of, it says something about how important the rules actually are, but nonetheless it works fine. So yeah, so to start off with, there's a lot of things in the headers. So I tried to look through my history to find the best resources for the PE header, because I was doing a lot of research. There's hardly anything. But yeah, I was trying to. I didn't find some of the best resources, but I found some good ones. And to start off with, this one. This one's not very detailed. It's more broad, but it does show literally everything. So yeah, this is the whole header, and I guess this could look overwhelming, but we'll be doing it all today. So to start off with, what we're going to be doing is making the DOS header. And as you can see right here, image DOS header. This is what I have open right now. This is the C version of the DOS header. You know, it's how the DOS header is written out in C, but we're writing it in C#. So to start off with, as you can see, there are a lot of words in this struct, and word just means 2 bytes, and in C# is the equivalent to a U short or a uint16. Those are both the same things. And what I'm gonna do is just simply copy down all of this information. But one thing you might notice is that there's these things that are arrays. But if I actually try to do that in C#, eres4, and I try to compile it, as you see, it won't work. And there is a way to do it, and that's what we're going to be doing right now. We're going to be setting up that. And the way you do it is you set it to fixed. And you compile that, and there's another error. Because it says pointers and fixed size buffers may only be used in unsafe context. So we have to set this to unsafe. Compile that, and there's another error. Unsafe code may only appear if compiling with unsafe. So what you have to do is go up here and right click your project and click properties. And go to the compiling tab. It should look similar on Visual Studio. If not, you can just Google how to allow compiling with unsafe code on Visual Studio. And then there should be this check that says allow unsafe code. You just gotta check it. And then now, as you can see, it compiles fine. So we were able to get that down. But anyway, all I'm gonna do is be copying down all of this data from this struct. And as I said, words are the equivalent to uint16s or U shorts. So start off with the magic ecblp ecp ecrlc. So I'm at here right now. ESS. And just so that I'm doing it quicker, I'm not putting them all in separate lines. I'm just putting commas. Which, if you have the same type, you can just put commas. ESP, ECSUM, EIP, ECS. So now I'm at here. And that's that's going to be all of them until the eres4. And the way we do the eres4, as I said, is you do the public fixed uint16 eres4. And then the next thing is more uint16s, single ones. And then there's the eres2, which is another array, so we'll do that. And then you might notice the final thing is actually a long. So longs, the thing is, they're not actually longs in C#. Longs have 8 bytes. What this is actually equivalent to uint32, or a uint, which is 4 bytes. I'm not familiar with the reasoning behind that. I don't program in C. As far as I'm concerned, in assembly, these are called double words, which makes sense because they're 4 bytes and a word is 2 bytes. But nonetheless, public uint32 elfander. And then now we're done with the DOS header or MC header. So I'm going to put it all in a region, which doesn't have any programming effect. It just lets me close it off. But before I do that, I'll let you guys copy this down in case it's kind of overwhelming. And yeah, so you can pause the video now if you need to like take a look at it or anything. And I'll make sure it compiles. And now I'm gonna close it off just so that it gets out the way. The next thing is the so just to show you guys what we've done, we've now made the struct fill in this much so far. That's how much it fills in right now. And as you might notice, the first thing in the MZ header is called the magic. Other people call it the signature. And that's the first 2 bytes. And if you look here, the first 2 bytes are MZ. So yeah, it shows the signature is MZ, which is, and it's called the MZ header. So you know, just to give you guys an idea. And yeah, we just filled in that much, and now we're gonna be working on this chunk right here, which is called the DOS stub. And the DOS stub is always the same, so I never bothered to really look up a lot of what it means, because it's always the same. So there's really no point figuring out everything if it's never going to change. So what I actually did, the first 14 bytes of the DOS stub, I quite honestly don't know what they are. But I do know that they're always the same. So what I can do is public fixed bytes unknown 14. Because I don't know what the first 14 bytes are. But what you might notice is after these first 14 bytes, if I select them here, on the right side you can see that this is selecting this program cannot be run in DOS mode. So as you can see, it's a message. And it's actually 38 characters. So message, and it's 38 characters. So at least you know what that is. The next 5 bytes, I don't exactly know what they are, so I'm gonna put them unknown 0. But the reason that I'm only making 5 is because the next 7 bytes are always empty. So I'm naming that unknown empty so that I know I don't ever have to change it. And yeah, that's it for the DOS stub. 14, 38, 5, 7. That should add up to 64, I believe. Yeah, so that's correct. And now what we have to do is close it off. I mean, I'll let you pause here if you need to, but that one's pretty straightforward. And now the next thing in the header, it doesn't actually give it a name here, but it's called the PE header, and that's kind of confusing because you know, you kind of think this whole thing is the PE header, but you know, there's a PE header inside the PE header, I guess. And this right here, it tells you all the information inside of it. Here it's called the cough header, which is not really what it's called, but anyway, call it the PE header. And as you can see, the first thing is the signature. So public uint32 signature. And the reason that we know it's uint32 is because up here, each of these things right here mean it's 1 byte. So this is 8 bytes. And this is cut off halfway. So 4 bytes, and the equivalent, and then the variable in C# that's 4 bytes is a uint32. And as you can see, it's always this number right here. Now the next thing is the machine, and luckily enough, in C# there's actually an enum that represents machine, but we're not going to use it. It's actually in the class, in a namespace called portable executable, but believe me, it's useless. I did a lot of research on it. But regardless, what we could do is we could write down this whole enum, and if you really want to, then go for it. But what I'm gonna do is I'm gonna create a new new class in my thing called machine. A new item in my project called machine. And the thing now, we changed it to enum, but as you notice in here, it's 2 bytes. So we have to declare that the enum is 2 bytes if we're gonna do it like that. And the way we do that is with ushort. It's I would do uint16, but it doesn't actually let you do that. Oddly enough, it expects for enums it expects you to do one of these. So yeah, we have to do ushort, and we could write down all of them, but there are about 24 of them. So all we'll do is set unknown, and then the one that we'll be using, which is the this one right here, Intel 386, so 32-bit, and is equal to 332. And now what we're gonna do is you could fill in the rest of these, but that would just take too much time, because this video right here is already going to take a lot of time. We might do it in a later video, but it's really not that important. But now we can go ahead and include it in our PE header. Public machine, and we'll just call it machine. The next thing is number of sections. As you can see, number of sections, and it's 2 bytes, so uint16. And then I'm gonna quickly just rush through the next ones. But the time, date stamp, pointer to symbol table, number of symbols is what I'll call this one. And then the next ones are 2 bytes, so public uint16, size of optional header, characteristics, and that's it for the PE header. As you can see, it's out of the green. And yeah, just looking at this, it might look really long, but a lot of this actually, for example, this entire data directories thing we do in 1 line. So anyway. I'll let you pause the video here if you need to see this. But anyway, the next thing is the it's this orange bit here. It's called the PE optional header. It's not actually optional, unfortunately. I had the impression that it was when I was first trying to figure it out, but anyway. As you see, it starts off with magic. I'm gonna really try to go through these quickly now. But the next things are the major linker version and minor linker version, which, as you can see, they're 1 byte, so that's why I'm doing them as bytes. And the next things are all 4 bytes, so I'll make them all uint32s. The first one is size of code. The next one is size of initialized data, and the one after that is size of uninitialized data. Then you got your address of entry point. Then you got your base of code, base of data, image base. As you can see, and these are both in the optional header. It's just organized weirdly on this graph. And the thing after that, section alignment and file alignment. And that's it for the uint32s. The next things we have are the uint16s. Major operating system version, minor operating system version, major image version, and minor image version. And then major subsystem version and minor subsystem version. The next things are uint32s, as you can see. Win32 version value, size of image, size of headers, and checksum. The next things are two uint16s, subsystem, and DLL characteristics. And the last things are uint32s. Size of stack reserve, size of stack commit, size of heap reserve. Now I'm right here. Size of heap commit, loader flags, number of RVA, and size is the last one. So yeah. Now for the last thing, the data directories. We don't need most of them. We just don't need most of them. I'll let you guys pause here and copy this down if you need to. But nonetheless, gonna continue now. Now the next thing is the data directories, and luckily there's 32 data directories. So all we have to do is make the fixed array as we did before for 32 data directories. The only ones we really even use are the import table one. So most of it is blank the whole time. And yeah. Now the last thing right here is the PE. They call it a section table. This is called the PE code section. And as you can see, so the there's a thing that's 8 bytes. So when you have it more than 4 bytes, look, you could fit 8 bytes in a uint64. But the thing with name is it's actually a bunch of characters. As you can see in this one, it's flat. You can change the name to whatever you want. It's generally the name of your programming language. So we don't actually make it a uint64. We make it a byte array with 8 bytes. And then for the rest of these, we do uint32s though, apart from these two right here. And for all the uint32s, I kind of just went through that as quick as I can because I know I'm running out of time, but it's virtual size, virtual address, size of raw data, pointer to raw data, pointer to relocations, and pointer to line numbers. So I'm really just copying it down the whole thing. And as you can see, these are uint16s. Write them down. And the last final thing is characteristics. Now this is the only thing I'm not going to be copying down word for word because we already have one thing named characteristics, so we have to put characteristics _0. Now, there is one last thing, which isn't on here, but luckily it's real easy to remember. Because all it is the import table. And these are uint64s that I'm doing. In other words, they're equivalent to ulong. Import table bytes, and it's just an array of 12 things. Compile it and see if it all went well. Shit. I don't think that's supposed to be there, to be honest. Okay, yeah, now we're in business. Alright. So, if all went well, I'm just gonna import this right here using system.runtime.interrupt services. If all went well, we can use marshal.sizeOf type of PE header, and it should be 512 bytes. And yeah, as you can see, the thing is 512 bytes, so you can check if yours is 512 bytes. If not, I'll really quickly open up everything and then just slowly scroll through it. So if you need to check it out, you can, because it is a lot. It is overwhelming, but this is the only big structure doing like this in the whole series. So and you know, it might seem tedious, but imagine how it was trying to figure this shit out without any trying to figure out, like, there's hardly any sources online, so it's really hard to it was really hard to figure it out by myself. But anyway, and it was even harder to actually figure out the data that goes inside of it, which is what we're going to be doing now. And this is another, unfortunately we're not done with the struct. We nearly are, but we do need to fill it in. And for filling it in, I'm going to have to explain one more thing. And the thing I have to explain is that, as I said, this whole thing is the first section, that's the PE header. After that, every single byte here is an instruction that like, it's either an instruction or it's like data. But right here, as you can see, there's only one instruction. It's called C3. And if you want to figure out what it is, I just put in olliedbg. And as you can see, C3 right here, and it's return. So all this application does is return. And if I open it up, as you can see, all it says is return. So these things right here are called opcodes, and that's what actually tells your application what to do. And that's why I have it called testing opcodes. And I'm gonna make another class just under this one called PE header factory. And whenever you have a thing called factory, that means it's just for creating PE headers or whatever it's creating, whatever it's a factory of. And so what we're gonna do is create a unsafe static public PE header new header. And in order to create a new header, you're gonna need a lot of data. And the data that we need is the I'm gonna have to import system.collections.generic. And I'm gonna close all this up. I don't remember opening it. I don't know what happened, but anyway. At least I thought I reclosed it. But anyway, the first thing we're gonna need is a list of the bytes. And as I said, every single byte here, for the most part, is an, or just, this is really generalized, but every single byte here is an opcode that tells you, the program, what to do. So we're going to need a list of every single opcodes. And then there's a section that goes, there's a different type of section that has opcodes in it, and this is for when you're trying to import things from a different DLL or something in your application, and it's just called import opcodes that we need. The next thing we need to create a header is the end mem address. Now if you now to explain what that is, as you can see, this number on the left here is the memory address. This is where all your applications are going to start. They're going to start at this memory address right here. And since there's only one byte, as you can see, the memory address would be this one, this right here, the end memory address, which is what we have right here. So we need to get that where it ends at, and then we're gonna need an offset, and I really can't explain what that is right now because it has no meaning right now. It only has a meaning later on. And then boolean GUI equals false. So this is just gonna say whether or not our application is a console application or a GUI application, and for now it's not going to be a GUI application. Start by creating PE header just with the default values, which is all blank, and that's how we do that. And I'm going to compile this and see if everything's fine. Alright, so yeah, we have to return the header. And yeah, as you can see, compile's all fine. But right now the header is blank. So what we have to do is, as you can see here, as I said, all sections are 512 bytes. So we have to make sure that we have to make a new list called mock opcodes. And so right now, this list right here, it wouldn't have the bytes filled in right here with all the zeros. It would just be that. It would just be that one byte. So we need to make a list that contains all of these bytes, even the blank ones, because we need that for some specific things in our struct. And then we'll just set it to this list right now, and then we'll say while mock opcodes.count modulus 512 is not equal to 0, and then add in a blank byte, and that will just fill it all in to the next 512. And now UN16 sections, and these are going to be all the sections of our code, but right now we're not going to have that many sections. The only sections we're going to have is if we have to import something. So if import opcodes is not null, then that's a whole different section on its own, so 2. But otherwise 1 is that logic right there. And now we can get into filling the actual headers, and this is going to be probably a lot of code, like 100 lines or so. So region MZ header, start with the MZ header. So luckily we don't have to fill in all the variables because there's some variables that can be left blank, but there are a lot of things that can't. So the magic, as I said earlier, you can see that the first thing is MZ. So what we do is we say bit converter to 2UN62, and I have to import system.txt. Encoding.ascii.getBytes MZ, and then the start index is 0, so we set that as that. And then the next thing that we have to fill in is ECBLP. This is the I believe it's the shoot, I think it's like the I could just check, can't I? Yeah, bytes on last page of file. I was gonna say current byte on last page. And the way that we check that is we take the opcodes and we get the count, and we just modulus it 512 because each page is 512 bytes, as I said earlier. I might have said section, but I meant to say page. And then the current page is or the pages in file. I'm not gonna actually explain all of these that much because this is a real long video, but that's math.ceiling, and then I have to convert it to decimal because when you're doing math functions, a lot of them expect decimals and return decimals. If you just roll over it for yourself, you could see. But and then I'm doing 512 I'm doing 512 because that's how many bytes are in a page. But the M means it's a decimal. And yeah, as you can see, what I'm doing is every page is 512 bytes, right? And we need to find how many pages there are. So we just divide it by 512. The next thing, we have to make a constant U.S.62 embassy header size. And as I'm pretty sure I showed earlier, it's 64, but we have to divide it by 16. And then the CPAR header, size of header in paragraphs, because we divided by 16 because of the paragraphs. So MC header size. E_min alloc, that's the minimum extra paragraphs needed. We don't need many, we just need that much. And when I do 0x, that just means I'm saying this to hexadecimal value. So this right here is equivalent to that. Now for max allocation, we want to set to the maximum value because we want as many as possible. As a stack pointer, initial, I'm pretty sure SP for stack pointer value. That's what we set it to. The LSR LC one. The file address of the relocation table. And then we do have to make some more constant bytes, such as the MC header size in bytes and the DOS stub size in bytes, which are both 64. And then the LFA new is the size of the MC header and the DOS stub in bytes. Now that's it for the MC header. For the DOS stub, now for the DOS stub, I don't even know exactly why a lot of these things are the way they are, but basically just copy over these bytes. You're gonna have to copy them down, but these are the first 14 bytes, and I don't know what they are. So, but what I do know is that what this is doing is it's creating a pointer to the header.unknown. So that's this right here. It's getting a pointer to that, so that's where it's going to copy it over to, is what it's doing. Now for the message, as you can see, it's this program cannot be run in DOS mode. So we could just set that to, okay, we can just set it to constant string, but you have to make sure it says exactly that. And then what we do is we select, I have to import link. We select every single byte, every single character in this message by doing .select, and then we convert it to a byte by just casting it. And then we convert all of those bytes into an array, because right now it's an IEnumerable. And then for the start index is 0, and then we create an int pointer to the header message as we did before. And then for the length, this time we could do message.length, because before we knew it was 14 bytes, now we know it's just the length of this. Now for the last unknown array, it's just some simple 5 bytes for the same reason as we did before, but this time it's unknown 0. And obviously after this we don't have to do the unknown empty ones, because we know those are empty. Now the next thing that we have to fill in is the PE header. Just as we did the magic for the MZ header, you do the same thing for the signature, except instead of MZ, you're doing PE. Because if you look up here, and you look at the start of the PE header, as you can see, it says PE. Now for the machine, as you guys know, we made an enum for that. Number of sections, we already made a variable for that. Now, time date stamp. This is actually what it means is the amount of time that's the seconds that have passed since 1970. So, the way we calculate that, we want it to be a unit 32 at the end of the day. And it has to be UTC based, by the way. So you have to do datetime.utc now, and then obviously we're subtracting. And then obviously we have to make a date time from 1970. So 1970, January 1st, nothing, no minutes, no hours, no seconds. Datetime kind.utc, because as I said, it goes by UTC. And then we just select the total seconds, and then we call it there. Header size of optional header. This is similar to how we did the headers up here. It also has a constant size that is just easier. And then the characteristics, this is similar to an enum, how we did the machine, except we didn't actually make the enum, but the value is this. Now we're doing the PE header. We have to do the PE optional header. And just like the other signatures, the other magic, as you see, magic, this also has one. It's just called magic though. And this is an enum, and the enum is actually called image nt optional header 32 magic. as you can see, it's the optional header magic. So that's what the enum is called, if you want to like look into it for whatever reason. The major linker version is 1. The minor linker version is 0x49. The size of code, this is where the mock-off codes we made comes into count. It's just the mock-off codes.count. The size of initialized data is equal to mock-off codes.count, and then we have to add in if there are import opcodes, then add them. If not, then don't add anything. And then we have to make a constraint 32 alignment. So what you might notice here is the memory address here starts at 401000. So that's 4 megabytes, but then it's plus an extra 1000. And that's actually the alignment. And then the image base is the 40000 part. And now what we have to do is create the address of entry point, which is just alignment, because as it starts at 4 megabytes, but then the alignment is where it actually starts at. So basically what we're doing is we're just aligning the entry point. Same for base of code and base of data though. Now the image base is obviously just the image base that we made. The section alignment is again the alignment. Now file alignment is different. It's equal to the size of one page, which is 512. Looking at that in hindsight, we could have made a constant for that, but it's okay. The major operating system version. The major, the minor subsystem version. The major subsystem version. These are just some constant values as well that I just didn't make variables of, but the major operating system version is equal to 1, and then the subsystem version is equal to A, and then the major subsystem version is equal to 3. Next thing we do is the size of image. Now, what we have to do is for every section, the alignment goes up. For every section in your application, it increases by the alignment. So what we have to do is set the alignment multiplied by the amount of sections. But then we also have to account for the header. So alignment. Add another one in, because that's not accounted for in sections. We don't add a section for the header. Header.size of headers. We could just set this to Marshall.size of type of PE header, which I did earlier in program.cs when checking the size of the header. Now we can actually use it right here to get the size again. And then the subsystem. This is where the GUI variable that we made up here comes into account, because the subsystem decides whether it's a console application or anything. So it's an enum as well. And if it's set at 2, that means it's set to image subsystem Windows GUI. And then if it's set to 3, as you can see, 3, then it's set to CUI, which is console user input. So again, we're just checking if we're making a GUI application. If so, say it's a GUI. If not, say it's a console application. Size of stack. Whoops. size of stack commit is equal to alignment. Header size of stack reserve is equal to alignment. Header dot size of heap reserve is equal to alignment multiplied by 16, and then header dot number of RVA and size is equal to 16. I wish I could explain this a lot more. But I don't want to make this video 2 or 3 hours long. So yeah. The next thing is, or the the second last thing is the code section. And as I said earlier, the code section, I believe it starts right here. But anyway, as you can see right here, you get the opportunity to put in the name of your application, or of your programming language. As you see here, it says flat. If I look on like my programming language that I made earlier, it says arrow right there. So what we're gonna do is, if you remember, in the code section, I actually made it bytes because we couldn't make it string, because it can't be a string because it has to be 8 characters long. So what I have to do is make another method in this class called another static one, because we're in a static class, and we have to make it a byte array because it has to return bytes to code section name bytes, and then we'll take in a string. And what I will say is I'll make the return value always returns 8 bytes. And the max length is equal to 8, as you can see. And then so that means if the string dot length is greater than max length, we're gonna have to throw an exception. And if the string doesn't start, the string has to also start with the period. That's another rule with a name. It's just how it is. There's not really anything to do about it. But yeah, apart from that, we're good. And then we have to start off by creating a list of bytes, and this is just the bytes we're going to return. And we're going to get every single byte in this string. And the way we do that is we select every single character in the string, but just by typing .select. And we do this, and then the X represents the character values of the string, and we have to convert them all to a byte, and we just do that by casting it over and convert it to a list. The reason we need it in a list is so we can do this. And what this is going to do, it's going to fill this list with blank bytes up until it's gonna, so they're supposed to, as you can see, this always returns 8 bytes. What this is gonna do is it's gonna see if this list has less than 8 bytes, it's gonna fill up to 8 bytes with blank bytes, and then we're gonna return bytes.toArray. And now we're gonna go back up here, and now we could actually use this thing. So we're doing marshall.copy again, and then you just put in the name of your whatever you want the thing right here to say. Just make sure that it's less than 8 characters and it starts with a period, and then you put .toCode set name bytes, and then start index 0. The pointer is going to be the name, and then it's always 8 bytes, so we can put it to that. Put the length to 8. The virtual size is how many opcodes there are. plus the offset. Now, this is going to be set to 0 for now, but it might have a use later, depending on how our programming language goes. So I'm not going to explain much, but as you can see, the virtual size is just the opcodes.count. That's what it means. And the virtual address, on the other hand, is equal to alignment again. A lot of things are equal to alignment here. That's why we made it a constant. Size of raw data. Now this one is the mock opcodes.count. So as you can see, the virtual size and the size of raw data are two different things. As I was saying, the two are different earlier. The pointer to raw data is 512 because that's the size of one page. And the other characteristics, this is another enum. So this is a uint32. So that's going to be 4 bytes. So 1, 2, 3, 4, and set that one to 6, and there you go. Now the last section is the import section. We're not doing any importing right now, but we will set it up for later, because I do want to get all this out the way so we don't have to go back to this. So if we actually have import opcodes, so if we are importing something, then first of all, we're gonna create a address, which is the end memory address, as I made up here, minus the image base. I really want to explain this. Alright, I'm gonna do it. So, as you see, as I said earlier, in this instance, in this program, for example, there's only one opcode, which is very small. So that means the end memory address is going to be this plus the opcodes count. And as you can see, there's only one opcode, so that makes it that. And the image base is always this. So what this is doing is it's getting the address without the image base. So now this would be that in this specific case. Now, what has to happen is we have to make sure it's aligned, and to align it, we get the address, we take the modules of the alignment, and while it's not equal to 0, then increase address. And as I said earlier, the address is at this point equal to like this, right? So now if we align it, as you know, alignment is equal to this. What this is doing is it's increasing it until it's a multiple of this. So it will turn this into that, because that's the next multiple. And that's what that's doing. And then for this, we have to edit the data directories. So as you remember probably, we made 32 data directories. Now the second and third one happen to be the import table ones. So the first thing it's just gonna be a pointer to the address. That's why we made it for. And the next thing is the size of how many import opcodes you have. So we could get that just by doing that. Now with the next 4 things here, for this one, we had to start selecting the import table bytes. And the first we made 12 right here, we made 12, as you can see. The first one is going to be we made them all UINT64s, so we have to convert something to a UINT64. And what we have to actually convert is encoding.ascii.getBytes.idata. And that's similar to how we made .demo or whatever, except it has to be .idata. It's just .import data. That's just the name of the label. And then we actually have to add in 2 more bytes, because this is 6 bytes long. A UINT64 is 8 bytes long, so we have to add in 2 bytes just by concatenating them. And then we convert that to an array. And then the next thing in this function in this method, it asks for a start index. Start at 0, start at the beginning. Now for the next 3 lines here, the unfortunate situation is I don't know exactly what the purpose of them is. I don't know what they actually are. But what I did do is I was like compiling applications a bunch of times, and I had like a table up, and I was just like noting down the differences to figure out what these things are, and I noticed that some of them stayed the same, and then other things were linear. So I was able to find the equations and the accurate values that worked. So I can't explain these much at all, but I will show you what to put down, just from my research, because I don't know myself, but I do know that this is the correct values. So I just wrote that down. I'll let you copy it down. It's just bitconverter.getBytes. You have to get the import opcodes count and then the address. So it's basically the same thing except reversed. But I'm not entirely sure why it's required, because we already give the information here, but it's the same thing except reversed. And then because these are both the UINT32s, which means they're 4 bytes. But this thing is is 8 bytes. So literally, this is the same thing as this, except it's reversed, because in here the import opcodes come first. It's just a different way to write it to account for the UINT64 instead of 2 UINT32s. Now the next thing, I couldn't. I don't really exactly know, but the first 5 bytes are 0 to 0, 0, 0, and the next byte is a linear value that I don't know exactly why it is this, but it is. I may have had a better understanding of it when I was actually figuring it out, but that was a few months ago. But this is just the equation. I don't know exactly the purpose behind it, but yeah, those are 8 bytes. As you can see, 1, 2, 3, 4, 5, 6, 7, 8. So yep, and then put a 0 right there for the start index. And the last thing here, finally. Is just a constant value. This one, I don't believe it ever changes. and if it does, then it doesn't break anything. So this right here you may say that a few of the things here in these, or like not these, but maybe like a few aspects in these two lines right here are kind of hanging onto a thread per se, except I haven't run into any problems with it. So yeah, those are the only things that are somewhat uncertain in this thing, but everything else works fine, or it all works fine, but everything else is pretty certain. But now we're done with this. Now we have to just be able to convert it into bytes. Luckily, that's very easy to do. It's basically built in. Create another static method that returns byte arrays, 2 bytes. This p header. So taking a PE header and convert it to bytes. And the reason we need to do it is because we need to be able to write the bytes to a file just like this. And we start with our header size. We need to define what our header size is. It's 512 bytes. And then we make an array with the header size of bytes. And then we create a pointer. And then we structure it. We add a structure to the pointer by structure to pointer. Take the header, we put the pointer, we just give the pointer a size. Oh shoot, I didn't give the pointer a name. I thought I did. And then delete old true Marshall.copy. Then we copy over. We copy over the header. I mean not the header. We don't do that yet. We copy over the array. We already did the header. And then we had to free h global. And with free h global, it's just going to make sure there's no memory leaks. It's going to free the previously allocated memory, unmanaged memory of the pointer. And then we can now return the array that's now filled with the bytes. And yeah, we're done with this class. We're done with this file for now, or I think for a long time. But now we have to make a simple application to test it out, and we also have to do something called calculating the checksum. So I'll just get that out the way right now. We have to DLL import something. Image help.dll. I doubt anyone's used this DLL before. I know it was my first time, and unfortunately, the fact that it's so unknown means that there's hardly any information about it. But luckily, I'm here to give you the information. So the method we're going to be importing is map file and checksum, which takes a string file name, and then it gives out a header, sum, and a checksum. So yeah, now what we're gonna do is create before we use the actual method, we're gonna create a simple thing to use our function here, new header, and as you can see, it requires a list, 2 lists, and then a memory address. And as I said, we're not using the offset yet because we don't need to. So to start off, we'll get the memory address. And as I said, it starts at this always, so we can set it to that for now. That's the memory address. It starts at that always, so we can set to that. And then we create a list. I don't actually have system.collections.generic yet. Well, we create a list of opcodes. The other list, which is the import opcodes, which we don't have any right now, so we set it to null. And we do actually need one more list called final bytes, because this is going to be the actual bytes we write to the file. Now for the opcodes, we're going to make it do the same thing as this application right here, which is just simply return. And as you see, the opcode's value is C3, so we'll add that. And you know, we're not going to be adding it just like that. We're going to be creating a better method to add opcodes later, but just for now we're going to do it like that. And whenever we add an opcode, we have to create, the memory address goes up, so we have to increase the memory address. And now what we're going to do, now that we have all the information we need for creating the header, we just plug in all of the information. The offset will be set to 0. And then while opcodes.count is not equal to the modulus 512 is not equal to 0. This is just the same thing we did right here with the mock opcodes. Now what we could do is final bytes dot add range header. So what we're going to do is just add the header. So we're adding this, we're adding the header, and now we're going to add the opcodes. So now we're adding this half. This adds the header, this adds the second half. And then like we might as well set this up if import opcodes is not equal to null. Well, then we would add them after, but obviously we're not doing that. And then we'll just create a constant string output file name and just make it some kind of .exe. It doesn't really matter, just whatever you want the output file to be called. And we can actually write to the file now. Oh, I need to import system.io. Right into the output file name. Final bytes, we gotta convert to array for this function to work, for this method to work. But now, as you remember, the last thing we have to do is calculate the checksum. Now this can only be done with this thing, and you need the file name, so it can only be done after you create the file. So we're gonna have to change the file checksum now, and we just open up the file that we just created. In a using statement, and we're gonna just calculate the checksum before we start writing, before we get in the using statement. So we plug in the file name, and then we're going to type out checksum twice. The reason we do it twice is because we don't need this value. We don't need the header sum. All we need is the checksum. So all it's doing is it's putting it in the checksum, and then it's just replacing it with the checksum value. I believe if you're on a higher version of C#, you can just do that, and then it'll work, but not on my version. So I had to do something kind of hacky, which is that. And that'll compile, and now we have to just write the checksum. And the checksum happens to be at 216 bytes in the file. I know exactly where the checksum is. I believe it's I just said I exactly know where. All confident, but I just believe it's right here. I'm not entirely certain. Let me see. Yeah, it must be that, because that's changing. So yeah, that's where the checksum is. So it's 216 bytes in, and we just set the seek origin to current. All seek does is it sets us to the the 216th byte, so we start writing there, and then now we'll write use on the file stream the checksum bytes just by getting the bytes using bit converter, and then the offset is 0. And as you guys know, hopefully by now, I really hope, uint32 has 4 bytes, and the checksum is a uint32. So 4 is the length. And yeah, if everything went well, oh, I did. It seems I made a little bit of a mistake right here. Get rid of dot count. Apart from that, we'll test it out. And now it should have. You can right click. You can open the output folder. If you don't have that on Visual Studio, I'm not sure if you do. All you're gonna do is go to your project in File Explorer, bin, debug, and then that's where it is. And then as you can see, if I open this in AllDBG, it does the exact same thing. It says return. And if I look at the bytes in this file, as you can see, it says demo. So, yeah. As you can see, it's just like this, except this one says flat, this one says demo. It has a different checksum. But as you can see, the opcodes are the same. And, you know, if I start, just to show you guys, this probably seems insignificant to a lot of you, but it is necessary for the application to start. And if I start messing with some values, like I'm not even paying attention to which ones are important, I'm just messing with them. I mean, I know this one is the date time, just offhand, but like, you know, like if I just start messing with the numbers randomly, eventually it'll just stop working. I probably don't even have to mess with them that bad. Let's just run this, and then as you can see, it runs right now. It doesn't do anything, but as you can see, it's opening for a split second. But let's try to just change something, like this is 0 value, or like just put it through here, see if that breaks it alone. No, it doesn't. But I don't know. I guess, okay, see, that kind of did something, but you know, really what I'm trying to say is that this is important. It's important that we got it all done today, and it was a really long video, but that's where I'm going to end it here. So I'll see you guys in the next video.